So I'm going to present you work I've done with Yannick, Forster, and Nicolas Tabareau on verifying an extraction procedure from Coq to OCaml. So our setting is Proof Assistant Coq, which allows you to verify software and mathematics. So you've probably known about the CompCert project, DeepSpec, or the four-color theorems that have been proven in Coq. And this proof relies on the proof checker of the theory, which should be consistent. But there is another part to Coq, which is extraction, which allows you to, from this artifact, to produce executable code. So typically, you will get a verified C compiler from the CompCert project, a verified web server in the DeepSpec project, or a verified coloring program from a constructive mathematical proof of the four-color theorem. So extraction is a really useful feature. And our work is to enlarge the trust that you can have in the verified artifacts, because right now the extraction procedure is just proven on pen and paper. But the artifacts, you would really like to trust that the CompCert compiler is really bug-free and that execution will always proceed as expected. So to do that, we have engaged in a project which is called MetaCoq, whose goal is to verify the main components of the Coq proof assistant. And it's been done before for the type checker and part of the extraction procedure, so the erasure procedure that I'm going to talk about. And today, I'm going to present you a different path through this project, which uses the malfunction project, which is a front end to the OCaml compiler, to produce a verified Coq to OCaml extraction. So we would like to give a good spec to the current extraction, but you have to look at how it works and what we can expect. So here I'm giving you a small example of a function that you might write in Coq. That's perfectly fine. Notice that it takes a function from unit to bool and returns a boolean, and it will call the function twice. Then I can extract this function. I get basically the same code in OCaml with a simple type, so it looks all fine. Then I can define myself in OCaml a specific function from unit to bool that actually returns false at the first call and then true. I call my extracted program with that function, and what happens is a crash. So something is amiss here. And what is problematic is that we have the illusion that the extracted programs types correspond exactly to the ones we had in Coq, but it's not the case. The function types are different in OCaml and Coq. Worse than that, actually I did not show you the implementation of this apply function or end function, but it uses ops.magic. So the extracted programs go outside the scope of the OCaml type system, so we have to resort to a pretty bad construct of the OCaml language, which is actually not part of the OCaml language according to Xavier Leroy, which is this ops.magic function which allows you to cast from any type to any other. So to ensure correctness, there are multiple solutions. We could try to manually inspect the code that is extracted and the way we interact with it from OCaml, but we have to be doing that thinking about the original Coq types the extracted code had, which is pretty hard. We could do dynamic checks at the boundary, but this is bound to be an incomplete procedure, or we could try to do static checking, but that requires restricting the way we interact with extraction. So the shift that we are doing in this work is to do away with types for the implementations, but keep them just at the interface. Because we know that extraction, while not correct at all types, there are some subset of types where Coq and OCaml agree. And typically, first-order inductive types without indices, so natural numbers, trees, basic first-order data structures, and functions between them, but no higher-order functions. And the theorem we want to prove is this strong interoperability theorem that any OCaml use of the extracted code will be safe, will not crash. And basically, we will extract untyped implementations, but be able to assign them OCaml types and be sure that the implementation is faithful to this type. So our contributions is a combination of the existing MetaCoq erasure and extraction pipeline, plus this implementation of malfunction in Coq, which provides us this verified compiler. So in this work, we've improved the erasure so that we could translate to an actual existing programming language and applied some practical optimizations. We have a formalization of malfunction in Coq, which gives us a non-typed OCaml compiler frontend. We verify, we describe the operational semantics of this language and show that the interpreter, which was written in the malfunction project before, can be ported to Coq, and that the semantics of the interpreter, the operational semantics and the interpreter agree. And finally, we have a realizability semantic for a subset of the Coq types, which can be translated fully to OCaml types, and show that the untyped realizers satisfy these semantic types. This allows us to show a separate compilation theorem, and this guarantees really total correctness at the interface between the untyped but verified Coq code and whatever OCaml code you want to write. Okay, so some related work. The KCaml compiler, which is a certifying compiler for ML that's implemented in HOL, which has a slightly different objective than this. There is an existing certicoq compiler from Coq to C, but it does not benefit from the compiler of OCaml, which applies many optimizations to a functional programming language. So it's a related problem also. And there is this UF project which compiles, but for only a subset of Coq, which easily translates to C. So I said in the context is that we work in the MetaCoq project, where we have already verified quite a bit of the meta theory of Coq. So the name of the calculus is Pickwick in MetaCoq, and we verified a type checker for this semantics, which should correspond to Coq. They are not exactly the same as implemented Coq today. Part of this work includes a formalization of erasure, which takes a term in the calculus of constructions and produces a non-typed term in the lambda calculus extended with a box construct that represents irrelevant information, and that also supports a match, fix, and cofix, so support for data types and co-data types. The idea of erasure is pretty simple. We will erase all the non-computational contents, so things that don't participate to computation of natural numbers, for example. So all types are erased, but also all proof terms, so objects P of type big P, which is a proposition. There is one particular point where erasure is subtle, is when we have an interaction between the propositional and computational world, typically when we eliminate an equality, which happens when we want to cast an object from one type to another. We are pattern matching on an equality value, but producing a computational value. And what erasure does is really just erase the cast, forget about it. So if I start from this Coq function, which implements reversal of a vector, which is annotated with types and coercions, erasure will really just produce computational content of just basically list reversal where we have indices around. Okay. So we've shown correctness of this erasure procedure, basically telling us that if in Coq I have a term T that evaluates in callback value evaluation to a term V, then the erasure of T will erase to an observationally equivalent value. And from this, along with all the meta theory we've proven in MetaCoq, we can show that if you have a closed term of type natural number, thanks to strong normalization, it reduces to an object N, which is irreducible. And thanks to subject reduction, it's also a natural number. And thanks to canonicity, it's necessarily one of two cases, either 0 or a succession of successors applies to 0. And by standardization, we can show that if we were able to evaluate T to N, actually to reduce T to N in any order, because the reduction is really not specified. We don't have an evaluation order in Coq. We have just pure reduction, strong reduction at any point. We can also attain the same natural number of just doing call by value reduction, with call by value reduction. Finally, this tells us that the extracted version of T will also evaluate to the extracted version of N, and they are equivalent. So the full pipeline that we have, starting from this erased language down to OCaml, includes quite a few passes. I'm not going to detail them today, But the main idea is that we start from a language that has the operational semantics close to Coq. So typically, when we want to reduce a fixed point in Coq, we must check that the argument of the fixed point reduces to a constructor before we can reduce. And no no practical programming language wants to do that. We don't want to do a check each time you want to unfold a fixed point. So we need to implement some translations that go closer to the operational semantics of a typical language. And again, these optimizations are justified because we have typing invariants. For example, for this case of unfolding of fixed points, we know that if we have a closed term of inductive type, it must reduce to a constructor. So this check is superfluous. We don't need to do it when you do weak call by value evaluation in an empty context. So this goes down to the malfunction language. And this is the abstract for the malfunction paper. It is a non-typed program representation intended as a compilation target for functional languages, consisting of a scene wrapper around OCaml's lambda intermediate representation. So the first untyped representation is the OCaml compiler. And the nice thing about malfunction is that we can benefit then from the whole pipeline of the OCaml compiler to compile our functional programs. So what we did is to basically verify the syntax of malfunction in Coq and port the existing interpreter. And we define the big step operational semantics with a heap and environment, because now we are really talking about OCaml-like values. So we have references, we have arrays. We show that, we produce during this big step evaluation values. So closures are blocks for constructors. So we have a different representation for constructors than what we have in Coq. We also handle the case of primitive integers and floats which were added to Coq recently and which are exactly the same in OCaml or malfunction. And then we have a proof that this agrees with the interpreter. So compiler correctness, we still follow the same forward simulation. If we have T which call by value evaluates to V in the erased language, then our compiler down to malfunction will also preserve observations. We can compose with the erasure correctness to get the same theorem for the lower level now. Okay. One thing which was not considered in our previous work on erasure is how do we prove a separate compilation theorem for our verified compiler. So what we would like is that you could compile a function T from nat to nat and separately an object U of type nat. And if this application was reducing to a natural number in Coq, then the application of the compiled components should also reduce to the same natural number in OCaml or malfunction. To do that, we need to actually define step index realizability semantics for a subset of OCaml types, so the first order function types and first order inductive types I was mentioning. So only for a subset of the Coq types. And we need to show that the functions that we compile from Coq are pure, they don't touch the heap, so that we can verify this theorem. Also, part of this theorem involves a readback function that allows us to decompile a malfunction encoded inductive value into a Coq inductive value, which we can reuse when we develop our plugin to interact with this extraction. So we have a plugin that basically runs the self-compiled verify pipeline I've just shown, which can link with a malfunction or OCaml compiler. And which allows to also link the generated code with some FFIs that implement primitive types like ints, floats, or arrays. We can also link the extracted code even to a Coq's messaging system if we want to write some kind of interactive plugins. And thanks to this readback ability, we can also develop kind of verified eval command that evaluates a closed term of inductive type to a value in malfunction and reads it back into Coq. And this part, the whole circuit has been verified. So by example, here I'm giving you some definition function n that I used in my previous example. I apply this function to true. So as you can see, the type of function n is takes a Boolean, but it decides depending on the Boolean if I'm going to return a function from Booleans to Booleans or a natural number. Clearly, this type is not expressible in OCaml. I can ask my plugin to extract this definition. So it will produce an MLF file, so a malfunction file. So it's S expression representation of untyped OCaml, basically. We also have a meta program that allows you to extract an interface for this for the functions you want to extract. So here it will find that what needs to be exported from this function definition is just the type of Booleans, and we are actually compiling a function from bool to bool. And this is one of the types for which we have the theorem that interoperability will be safe. And we could also run, thanks to this readback translation, the function apply to false to produce a Boolean in Coq. Finally, I'll talk a little bit about benchmark and evaluation. So with respect to the existing Coq extraction, as soon as we enable optimizations in the OCaml compiler, they are pretty indiscernible. The existing unverified OCaml extraction or extraction through my functions. Compared to certicoq, we are in a bit better shape here because so on the left side, the blue bars represent the performance of our new verified extraction with optimizations applied in the OCaml compiler, and on the left side you have various runs with certicoq applied with we're using either GCC, CompCert, or Clang to compile the C code that is generated by certicoq. In this case, we are always better, but it's to be expected because the CompCert C compiler is not really designed to compile a functional language, whereas the OCaml compiler has been made for that, of course. Okay. Some future work. So we have been looking at how we can use extracted Coq functions from OCaml, but there is also a common use of extraction, which is to use this extract constant directive, which allows to call OCaml functions from Coq. And this we have not considered. But to do that in a proper way, we really need to have some kind of program logic for the external world, for the malfunction or OCaml world. And there is a project going on based on Iris doing that. And we've found that actually we can verify most of the interesting translations done to a usual programming language, except for cofix points, where the fact that we can translate cofix points to a use of lazy enforce, so thanks, is actually quite complicated and requires some invariant from the guard condition of Coq. And that's it for me.
Time for one or two questions.
Yes, thanks, Matthieu. I was curious, what is the formal semantics for malfunction? Does it have one? How? I didn't understand what was the formal semantics of malfunction.
So they were not formal. So basically, it's the scene wrapper around OCaml plus an interpreter that has stricter semantics than your OCaml compiler. Up to now, it's been true that it held. So you can inspect the interpreter and convince yourself that it corresponds to the semantics of the OCaml compiler. But as there are no formal semantics of the OCaml compiler, you only have, some informal trust in you can only have informal trust in it.
Could you have written yourself a specification in Coq for malfunction and try to prove that what you generate is correct with respect to that semantics?
That's basically what we did, but we wanted to start from the expertise of someone who knew the OCaml compiler and actually wrote an interpreter thinking that it would really model what the OCaml compiler is doing. So that's why we started also from the interpreter of malfunction.
Makes sense.
Real kick, please. Sorry. Real kick, please. Real kick, please. About the education.
Quick, I guess.
Yeah, I was actually also wondering about the semantics. So you mentioned at the beginning that basically the old thing used object.magic, which exposes lots of internal details of the compiler, so it's hard to reason about. So instead now you use malfunction, which exposes even more internal details of the compiler.
Yes.
And somehow that's easier to reason about. Why?
I mean, so the first version of extraction, actually it does compile to an untyped language. It just tries to type check back these untyped terms, try to type them maximally, and when it fails, it inserts object.magic. That was the whole procedure of extraction was doing. So we never managed to really reason on the object.magic annotated code. We either reason on the, we always reason on the untyped realizers.
Okay, I might have more questions later. Thanks.
Let's give him a big hand.